Hello, everyone. We'll be starting in just a few minutes. I'm just going to leave a couple of minutes for everyone to join the meeting. Okay, I think we should get started. So good afternoon, everyone, and welcome to the University of San Francisco's MSDS seminar series in data science. I am Sean Butcher, the Partnership Director for the Data Institute, and I want to wish you all a happy new year. I do have a couple of announcements before we begin. If you look on the slide, there we can show details. We have a data ethics certificate beginning on March the 23rd, and you can register for that at the address given. I also want to remind you that March the 1st is the deadline for the applications for the data science programs 2021 to 2022 cohort. Before we begin, I want to draw your attention to the Q&A button at the bottom of your screen. We'll leave some time at the end of the talk for your questions. So if you have any questions, please type them into the Q&A section. Today, I'm pleased to welcome Vedant Dhandhania, a lead scientist at BSG Digital Ventures, who will be giving the first seminar for 2021. BSG Digital Ventures is the corporate innovation and digital business building unit of the Boston Consulting Group. At BSG, Vedant spearheads their machine learning programs, and in today's talk, he will be covering some of the best practices in recommendation systems. Welcome, Vedant.
Hey, thanks for having me, everyone. I see more than 100 attendees, so I know it's lunchtime. You guys are hungry, but I hope you guys can run through an hour with me. I'm gonna try to make this super collaborative. It's not gonna be extremely technical, so don't be super scared. We'll try to go through several discussions, and then feel free to inject to, like Sean mentioned, feel free to raise questions in the Q&A. The hope is at the end of the talk, you guys learn something that you guys can deploy in real life. Just by show of hands or a few people, can you guys see my screen? Awesome. So that looks like people can see the screen. A quick intro on me, Sean. Thanks for those kind words. I started off my career in Germany, worked at Fraunhofer. This is where the MP3 was created. Moved to USC to sort of work on audio and machine learning stuff. This was back in 2011, 2012. And then for the last 8 or 9 years, I've been kind of almost building recommender systems. I've worked at Retention Science. It's one of the leading startups providing recommenders to marketing teams. I also worked at Boston Consulting Group, specifically for their digital venture arm, incubating a lot of startups within Fortune 500 companies. Currently, I do work at Apple, a small change in employment over COVID. And then, back to the screen again. Just give me 1 second. Small. Hmm. Okay, can you guys, I think I'm back now. Let me go back. Cool. So that was enough about me. You guys can reach me out on LinkedIn or email. We'll be sharing the slides after the talk. When I say rec engines, like what's the scale that we're looking at? We've basically built this out for hundreds of companies, both Fortune 500 and startups. The volume of data is more than thousands of data points per second. So it's actually built at scale. And then we've deployed on production more than 1,000 machine learning models that cover recommenders. We've hoped to track almost every person on the internet, both in the United States and the European Union, and we've basically powered more than 1 trillion transactions on the web, specifically related to ads and recommenders. Here are some of the clients that we've sort of deployed. So if you've probably read the news on LA Times, there's a good chance that I've shown you that article to read. Next slide. What we're going to cover up in the next 30 to 45 minutes is I want to sort of define the problem statement in very simple terms, figure out like, how you should start about building such recommenders, go into more of the machine learning aspects that you guys learn in your data science lectures, in your classes, and see the practical edges to it. And then sort of end with some red flags, with some visualizations and so on. Now, almost everyone's well versed with what recommenders are. If you're on Tinder, you probably get a match from some recommender algorithm asking you to go on a date. If you're on Amazon, you've been told to buy something. They're sort of ubiquitous. Like right now, with all the GameStop frenzies, if you're on Robinhood and you want to buy a stock, there's a good chance Robinhood is sort of asking you to buy, recommending you some stocks to buy. So almost every company has this problem where they want to assign certain users certain set of items. Now, the definitions of users can change, the definitions of items can change. So this is just a placeholder. But in all practicality, the problem boils down to what is sort of the definition of best, and what is the best item to show a user at a specific time window, a specific session, and so on. Um, So let's say Amazon has a few million items and a few million users. If the user had to explore all the items, it would be extremely hard for the user to find it. But now you have an AI system, or like a statistical system that can figure out that, hey, Yanit likes soccer, so let's show Yanit a soccer ball, versus Sean likes basketball, so let's show Sean a basketball. And what this helps is it helps you to find the item quicker, purchase it quicker, and it leads to ROI. And because there is a monetary aspect to this, that's why there's so much of research interest, so much of money and talent poured into figuring these systems out in different conditions. So before I go into the more details, with a show of hands, does this sound good for everyone? Everyone understands the problem statement. Everyone understands what we're going to discuss in the talk. Awesome. Cool. So whenever we start off with recommenders, right, like what we've learned over the years is you got to always start with simple rules, because even like deep curated AI is nothing uh, but a series of complex rules. So let's say you're on Amazon and you've been shown this nice toy. There's a good reason that you've been shown this toy, because you're 26 years of age, you're living in San Francisco, you probably are like playing tennis or something, and you want to buy a toy that correlates to tennis or something. So even though the rules are fairly complex, you can get really far with like really simple rules. So I'll give you one example. Like when I worked with CNN and LA Times and so on, the the latest item in your newsfeed, or the latest items that are coming out by the journalist, are usually the best recommended items to almost any users. So instead of like curating a really hard machine learning algorithm, you can get really far by a simple rule which says that, hey, the latest news that comes out with the journalist, right, let's recommend that. So if Trump is tweeting something, it's good chance that, if I recommend that, that's going to basically have a really high ROI, just because it's like the newest, the freshest news. Similarly, like if you go to Netflix and you look at Netflix's is baseline algorithm, it's essentially the top 10 viewed shows on Netflix. Now, there are certain caveats and shortcomings of such simple systems, but what they do is they give you more pros than cons. For example, these systems are typically used as good, strong baselines. So when you pour in millions of dollars in constructing really advanced systems, you need to measure what it would compare with as compared to simple rules. Also, machine learning systems follow complex engineering uh, sort of topologies. So whenever these engineering systems fail, these simple rule-based systems can act as a backup generators for the more complex systems. So sooner or later, you would have the need of a backup, and that's where you actually leverage these. Now, these are also very scalable and fast because you can make an algorithm with a simple rule in about 10 lines of pandas code or SQL code or whatever you love writing. And they also have really strong mathematical trade-offs because when you actually break this down into sort of the AI formulation, there's usually a model which models the prior, there's usually a posterior. So these simple rules have strong business priors, they have strong business uh, rules, and they usually stand the test of time. So here's one A/B test that I did in 2016 with a simple Fortune 500 retailer. Now we started off the engagement with a simple bestseller algorithm, and we said, hey, we're going to curate a bestseller algorithm. A bestseller is something that brings in enough volume for the client as well as enough revenue for the retailer as well. And what we want to do is we want to get this to production to the users within 10 days. And then we measured, like, when we showcase this recommendation algorithm, which is really simple, took us only a week to build, it basically gives us a click rate of 2.53%. So out of 100 people, 3 people click on it, which is really, really good. And then about 0.8 people out of 100 people end up buying something that we show. And the latency is 21 milliseconds, so it's really fast and snappy. So if you're on your iPhone and swapping on the app, you can get much more fluidity with the interaction. The UI UX looks really good. Now, fast forward 8 weeks, we have a really well-known model called the factorization model. I'm not sure if you guys have learned this in your class, but it takes us about a week. It takes about a month or 2 months to get to production, and the lift that we see is not it's good, but it's not like obnoxiously high. And then the latency, you see, like, these models are usually slower, so there is some trade-off. So whenever you guys go out in the industry, you guys are told to build these systems, always think about the practical app side of things, like, what's a simple system, and then use those systems to actually build on top of those systems to actually build something more advanced. Measure trade-offs, like, how complex it is, how much time does it take to compute it, how much money would go to building that out, and so on. I think I have a Q&A. Let me just see if I can. Oh, I can't access the Q&A. Weird. Sean, can you access the Q&A by any chance? Oh, Subos. Super, thank you both.
Yes, there's nobody's asking. We answered a question, so there's no pending question there.
Cool. So the sort of lesson learned here is, start with these simple rules that you think make sense for the business, whether it's a news company that you're working with, whether it's a dating app, whether it's an e-commerce company, whether it's multimedia. Think about, like, if you were a user, like, what's some of the simple rules that explain you how you would like some content or some items to be recommended. The next one is Amazon. Here's a good example. One of the classic rule-based algorithms, which comes under the collaborative filtering family right now, but when it started off in 1995, they were a book retailer. They had this odd rule, like which was if a person like Janet has read book one and book two, and I'm a friend of Janet and I've read book one, then there's a good chance I should be recommended book two. So if you've seen Titanic and Ben-Hur, then there's a good chance that if someone has already seen the Titanic and not Ben-Hur, let's recommend them to Ben-Hur. What this is called is, hey, customers who bought this or read this have also read that, and so on. So you guys get the point. But now this simple rule has now exploded into this family of collaborative filtering, and you can have various flavors. But it's still one of the golden sort of baselines to beat. It's definitely one algorithm that's still brings in almost 20% of Amazon's revenue. They have a few advancement, but the core gist of it still remains the same. Uh, Facebook's last link targeting, which again is responsible for more than 25% of their ad revenue, is really simple. It's nothing fancy. Even though Facebook has about thousands of machine learning engineers, one of their really powerful algorithms is just a simple rule, which is, hey, if you go to a website and you come back to Facebook, they want to target you with the last link that you visited. And it's sort of like a good attack on human psychology. It's essentially telling you that, this is something recently that you were interested in, so let me show you that again. So I wanted to visit San Diego over the break. Not a good idea with COVID around, but as soon as I went to Facebook, I actually saw uh, Visit San Diego as a sponsored link, the same page that I visited 10 minutes ago. And because humans are typically, they think in the same way, they act in the same way, this usually leads to good psychological priors in showing recommenders. Now, you guys can definitely now understand that when humans interact with these systems, you can now sort of decipher what's happening under the hood. What are the data requirements that needs to go into this to basically come up? So one good exercise for everyone is, whenever you guys see these recommender systems, try to uncover as to what's happening behind the scene. How did this is nothing but a person's algorithm. How was he able to show you this or that? I'm pretty sure you guys sometimes wonder and sort of think it's creepy as well. But a lot of times that creepiness is literally solved in a few lines of code. It's the ability to track you over different devices, different web pages, that sort of leads to it. So now this is also evolving into an ethics issue, into a sort of privacy issue as well. But the core algorithms, right, from the mathematical formulation, still remains very simple. Uh, Now, next, we talked a lot about rules-based recommenders, but if you want to do machine learning, all of us know that there's a concept of features. Uh, Features are essentially the backbone of any model, whether it's a neural network model, whether it's a classifier model, whether it's a collaborative filtering model, and so on. You want to represent users and items with some machine understandable numbers. These numbers are typically vectors or tensors in large dimensions, and you as a machine learning engineer or a data scientist have the ability to teach the machines what these features are. So some are hand curated, some are latent, some are also driven by heuristics. So we in the whole family of recommendation systems, we have all features can be divided into three kinds of features. The first feature that you see on the left is the user features. So uh, uh, let's say the person over here, Johnny is a person from Chicago. He's 29 years of age, and he's, let's say, got a master's in mathematics and so on. So what you can do is you can represent Johnny by a set of numbers that represents some of these characteristics about Johnny. Usually these features are gender, age, the device that you're using. So the more data that these companies can get on you, the larger they can profile you. But this is only 1/3 of the tracking. There's another component to it, which is the items. So imagine Netflix gets a movie, which is The Queen's Gambit. That typically becomes an item. And you, as a user who's watching Netflix, uh, uh, Netflix also needs to do the same on the Queen's Gambit, which is how long is it, who's the director, who's the star of the movie, what genre is it, does it have any comic relief, is it drama, and so on. So all of these features that represent the item in this case, which is the movie, you also need to like curate features about it, and these features are usually vectorized such that the machines can understand, because the machines can't really understand that, hey, the Queen's Gambit is a movie about chess. So usually the feature goes like, hey, is the movie about sports or is it not about sports? So it's usually a binary variable, like a 1 or a 0. Now once you have these items, item features and user features, these typically are static. That means that if the Queen's Gambit is a 150-minute movie, then there's a good chance that it would always be a 150-minute movie. So these are static. These are not changing over time. If Johnny is a male from Chicago who has a master's in mathematics, there's a good chance that these features are not going to be uh, changing over time. Now, you obviously need a dynamic component to these vectors, and that's where the user item features come into play. So everything that you can mine, which is an interaction of a user and an item, this forms like additional inputs to the AI. It could be like, hey, which movies did the user watch, or which items did the user buy, or how did you rate or leave a comment on an item. If you're like a Yelp, if you use Yelp, if you go to a restaurant and you mark it 5 stars, that could also be a dynamic user item feature, which is like, hey, Carl over here went to let's say Subla, he bought some salad and he marked the Subla service as 3 stars. Uh, so when you actually build on it, you actually can represent this cardinality in a very very high dimension. Uh, now, I'm emphasizing on this because most advanced systems require you to create this, and most of the Fortune 500 companies, they have large engineering teams, which gives you some of these features. These features are computed on real-time basis, and these are usually in the thousands of dimensions for each of these three families. Now, uh, one golden rule that I've learned is the features and the data is much, much more powerful than the models and the algorithms. If you actually get your features wrong and your data wrong, then everything else that you do downstream is sort of not effective. It's the classic GIGO, which is garbage in, garbage out phenomena again over here, which you commonly heard in your classes or in a lot of other talks. But that really, really holds true in recommendation engine. So a lot of teams are involved in data security, data sanity, data cleaning, data engineering, data feature engineering, data availability, real time sort of crunching of data, and so on. One golden rule that is very prevalent in today's data engineering philosophy is you want to keep the features simple. You want them to be easily understood in your organization. So uh, if you have a complex feature, let's say, hey, the feature is this a person belonging to cluster 6, and nobody knows what the definition of cluster 6 is, that's not a good feature to have. But let's say a feature which is, hey, is this person's income more than $50,000? Yes or no? That's a very easy feature to understand. So make your features very easily understood by everyone, and that's going to help you uncover a lot of things in your algorithm as well. Uh, Now, I sort of pointed out earlier, which was taking Sean and Sean's love for basketball's example. Now, a user feature for Sean could be his location, his sign up, what credit card he uses, who are his friends, and so on. There are some dynamic components to Sean's features, but typically user features are very, very static. Similarly, if he likes the Spalding basketball, which came out in 2019, the new model, then you could have different information about this basketball, like what's the price, what's the category, vendor, is it coming from China, is it locally manufactured, what's the description, and so on. And then the last part is is capturing Sean's interactions with this specific item. Did he swipe it? Did he add to cart? Did he leave a bad review? Did he do this or do that with the specific item? Now, if you think about the combinatorics, if you have millions of items and millions of users, this user item features typically expands to some crazy dimension, which is not even fathomable even with modern compute systems. So there needs to be some sort of mathematical formulation that reduces this whole user item interactions, for the lack of a better word. This is typically done through using several algorithms, which you guys must have read in class or must have explored in literature. We're not going to cover most of those nitty-gritty linear algebra techniques, but the whole idea is how can you teach machines some of this, show them a bunch of user item features, and then have the ability to for the machine to answer, like if Sean was shown a tennis ball instead of a basketball, what would the chance be that he picks up tennis or that he actually goes and buys the tennis ball? Awesome. So any questions before I go into construction of some models?
Yes, Johnny Costello had a question. How do you measure if a rec is effective?
That's a great question. So typically the evaluation of the recommender comes through business teams. They are one of three categories. Either they are in the engagement category of things. So think about KPIs, key performance indicators for click rate, open rate, or like interaction rate or add to cart rate. These are classically not revenue based, but it measures how much does your algorithm contribute in engaging the user with your content or with your item. The second family is revenue based, which is typically the the end goal of most recommender algorithms is to sell you a subscription or sell you an item, and these are represented either through revenue or through buy rates or through volume of items sold. And then the last component is usually more uh, long term, which is lifetime value based or like length of subscription based. So a dating app with a really good recommender will likely have someone in the app for a period of 30% longer. So it's hard to quantify an exact attribution to the recommender model, but a lot of these systems also require long-term reward components and short-term loss components. Um, Now, uh, the sort of harder question is, uh, you really can't evaluate the recommender in its truest form without having pushed the recommender to a live set of people. So typically how you do that is when you actually go live with a new model. Let's say Johnny came up with a new model, let's call it Johnny's recommender, and he works for Netflix. So what Netflix would do is after they would uh, understand the sanity of Johnny's recommender model one, they would expose that recommender model to a small set of control group, and be able to evaluate some of these metrics that I mentioned to you earlier. The metrics are usually defined earlier through the business team collaboration, through the product manager collaborations, and so on. And then they're going to run this on, like, let's say half 1% of the population and see how good it becomes. Now there is a new blend of science that does offline evaluation, where even without going live with this, without going live with Johnny's recommender, you can in an offline way predict how it's going to be, and that usually comes with a small lower bound and upper bound of errors. But the goal is like, hey, how do we reduce the risk of going live with something? And this is one of the hardest thing. Evaluating a recommender and A/B testing a recommender, which we'll come to it later, is actually harder than building the model itself. I'm not sure, Johnny, did this answer your question? Awesome. Sean, I can't seem to, because I'm sharing my screen.
Okay,
I can't.
it's okay. I can read the questions to you,
Yeah.
or do you want to leave them to the end? Because
We could possibly take like two more.
Okay, great. EJ asked, how do you avoid adding features that overlap? So for instance, features that are correlated to each other, or is there no problem with adding many features that overlap?
Yeah, so this is where the art comes into play rather than the science. Uh, uh, what I've learned over time is there's no one rule fits all. You always want to make it incremental. You want to start with small dimensionalities that you truly believe is indicative of some outcome, and then gradually build on top of them, because then that gives you the ability as an artist, as a data scientist, to control the evolution of the algorithm. Usually the other school of thought is they you want to throw everything at it and then use some statistical methods to figure out what sticks on the wall and what doesn't. I'm not a super big fan, but that's like the sort of lazy way out in building some of these systems. And then to answer your question, there's usually a really strong belief in less is more in some of these cases, because a lot of these features come up with a lot of redundancy, and you're essentially overloading a lot of systems that would imply the same information gain. So, for example, if you have a feature which is what is the price of the feature, and then you have another feature which is like, okay, which country is this product coming from? You know, all the French products are like comparatively expensive as compared to the Canadian products. So you don't want to throw everything at it. You want to think, what are the orthogonal dimensions that I can think, and there is a point of diminishing returns. Once you go past beyond like a few hundred dimensions, uh, the complexity to add more dimensions is extremely high, and the ROI is in there. So there's no like one answer to this question, but think about like the practicality of some of these ideas. I'll take Claudia, and I can see Claudia's question. Uh, it's Yeah, so Claudia, this is a great question. So if I understand, you usually struggle on Amazon, like they're showing you the same things. They are essentially giving you things you've already bought and showing you stories that are sort of hitting on your dopamine effect by showing you something that you would like to read, and so on. So I've got a specific section for this, so I'm going to answer this in my incoming slide. But this is a great question, and obviously these companies know these problems exist. And they have practical solutions to ask this to assess how deep these problems are. So let me quickly go to that slide to answer Claudia's question. So what for everyone's sake, what Claudia is asking is hey, Netflix usually recommends me some stuff that I've already seen, or Amazon showing me stuff that I've already bought. Now here's one example of Walmart. So when you go to Walmart, here's their emails that I get, and you see like I'm getting more of the same item. I'm getting Kobe's Nike shoes, and then I'm getting another Nike Kobe shoes the next day, and I've already bought Nike Kobe shoes. So this problem is called the temporal deduplication problem, and it's usually a side effect of AI being greedy, where AI does not know that you've already bought it, but it's pointing out something that's already occurred. So you can classically fix these systems by incorporating a business rule, where you can take some of these ideas that Claudia said, and sort of overlay that. So it's not super greedy. Similarly, Ralph's, which is a grocery store in LA, I just signed up to experience this problem. I know I buy milk and bananas every time I go to Ralph's, so it's like, why am I getting milk, bananas, and tomatoes every time I get a recommender? Now, on the face of it, the recommender is correct. It is exploiting an objective metric, which is me buying something, but it doesn't know that there is no bottom line increase in the sale of Ralphs. This problem is commonly known as the Miley Cyrus problem or the banana problem, where earlier back in the day, Spotify would only recommend you Miley Cyrus. Why? Because it's something that you listen to over and over again. Not that I'm a Miley fan, but it just happened to stick with that. It's also called the banana problem in brick and mortar sales, where If you go to a grocery store, you'd always get recommended bananas because it's one of the most selling items. However, how you fix this is by incorporating an objective function, which is exploration in your AI, where your AI is not only capturing the exploitative purpose of showing you items and helping you buy items, but also the ability for you to see more content, see a diverse thought of view. It usually comes at a cost, but there is a sweet spot where you can explore and exploit at the same time. And this classically is called the bandit problem, where can I use the Nike Kobe space and show you something different. Awesome. So let's continue with this talk and keep the questions coming in. I did uh, we did jump a bit ahead because of thanks to Claudia's question, but let me get back to the models. Now, whenever you whenever you get a rec problem, there'll be hundreds of problems that can be boiled down to a rec problem. There's a classic saying in the AI community that every problem is a search problem, but but every problem can be a recommended problem as well, because recommended problems are boiled down to search problems. So think about, like, you getting an Uber ride is also a recommended problem, because Uber needs to decide which is the closest driver that needs to be recommended to pick you up. uh, when you're swiping through Tinder, which is a bad example here, but Tinder is trying to recommend you something. Like, so the whole basis of the business model, or the value prop that they're trying to get you is helping you choose, or helping you select, or giving a service to you which would otherwise be really, really hard. Now, the two types, how they usually do this is either they take a content based approach or a collaborative approach. And the modern way is to mix and blend both of these approaches. The content based approach is fairly simple. It basically harnesses content of the users and items. So let's say a good example would be, what are the top items in the furniture category. Now, this is a content based model, because you need to understand which items are connected to a category. You need to have that information about that content. So if you don't know which chairs are attached to which furniture category, you cannot use this. Top items in user demographics is another one. So let's say you're living in New York, and it's super cold, and you're male, and you're 65 years of age. There's a good chance you'll be recommended Bernie Sanders mittens or something. So this is, again, like, you need to come up with these the content, or which is also an attribute. You need to understand what attribute does the item belong to, and what attribute does the user belong to, and connect these two. uh, they usually have the local minima problems, which Claudia just described. If you get recommended the mittens, there's a good chance when you come the next day, you're going to be recommended the mittens again, because it does not have any sort of knowledge as to how your evolution or relationship with the mitten has evolved. Uh, but these are super effective algorithms, because they cover a really good business rule, and they're easy to explain. So if a user asks, like, hey, why was I recommended a pair of mittens, you as a scientist can easily explain to the user that you were recommended this mitten because you live in New York, and you're 65 years of age, and it's super cold in New York right now, and everyone's buying mittens in New York. And that basically would add to a lot of headaches from the compliance side, um, from the social aspect of these recommenders. Uh, However, you do need some business acumen to come up with that rule. You need to define content for both the user and the item. The second one is collaborative based. This is typical to the algorithm that we discussed with Amazon. Like, people who bought this also bought this is a classic collaborative filtering algorithm. This has no idea on what the item is. It has no idea what the person is. So when you think about, if Yanit has seen Ben Hur and Titanic, and I've seen Titanic, then I would be recommended an addition movie, which is Ben Hur, because whoever watches Titanic also watches Ben Hur. Now, when you think about this, the AI never had any understanding of what Titanic was. or what Ben-Hur was. It's two completely different movies. The only thing that connects them is they're like really, really popular, and everyone likes to watch like movies that have won a lot of Oscars and a lot of academies and so on, and they're like really long. So the latent factors that connect Titanic and Ben-Hur is exploited by mining the behaviors of the user. So the brain in the user's head was now somehow captured in these latent hidden properties. Now, these are obviously harder to explain and control, right? You don't know why a person would watch Titanic and Ben-Hur, and why would you and how would you exploit that pair or that decision making? But what happens with these systems is there's a higher chance of exploring, like, because I've already known that you watched Titanic, you actually get to see a new movie, and this has good business sort of priors, uh, uh, because these pairs occur with high frequencies. Now, even the modern neural network based formulations are very similar to this. It's just that they take some of these collaborative filtering based approaches, and they supercharge them with a lot of data, and they formulate that through some deeper pairs and deeper mechanisms that is not fathomable, that's not understood by just counting pairs, or explaining it by a rule of people who also bought this and also bought that. So that's where the modern trajectory of Amazon and Facebook are going, like deploying these deep learning systems that can exploit the collaborative nature of this problem. uh, Now, this was again a question from Johnny, I believe, early on. It's like, how do you measure it? Like, how do you measure if you come up with an algorithm, whether it's a modern neural network based recommender, or whether it's a simple classifier, whether it's a collaborative filtering algorithm? There's a classic saying, which is, if you can't measure it, you can't improve it. So there is a bunch of metrics that you want to optimize for, the same three families that I mentioned. One caveat that everyone should be aware of, like, if your results are too good, it's probably lies. There's some underlying bias in your evaluation. What I mean by that is, there's one classic example in 2015. Was working with a client, and it was one of the biggest fitness providers in the US. And we basically switched out the algorithm and compared it with what they're running, and we noticed like a 3x increase in some of their redemption. And we thought that, hey, our algorithms are super powerful, because they made everyone join and buy these protein bars and buy these gym subscriptions. But what we didn't realize was that, it was primarily because uh, there was like a social media sort of challenge that was going on, where everyone wanted to do 100-day gym challenge. And that sort of made our algorithms like super favorable as compared to the baseline algorithms. And usually this didn't lie this would not have sort of followed the test of time. So whenever you're seeing really good results with whatever recommender you come up with, always be sort of skeptical of its success. You want incremental improvements, but if they are drastic improvements, both good or bad, that means that your split populations, or the way you've been A/B testing, has a lot of biases. Now, there's the bias itself. There's more than 25 types of biases in recommender systems when you're A/B testing them. I'm not going to go into all of them, but some of the common ones that I just described were the temporal biases, the group biases, where your recommenders are being shown to a much more better and cleaner population as compared to the other algorithms. So you want to split them like equally, like apples to apples. There's a lot of algorithmic bias as well. Like I mentioned, Facebook's last targeting is an algorithm bias. There's a bias in the algorithm because it typically uh, is only available for people who viewed a page recently. So they are more engaged with Facebook, and hence those recommenders do really well. So there are different ways you can reduce the bias. You really can't eliminate it until you have like an infinite population size, but there is a good trade-off where you can reduce it substantially, so the bounds of the errors are reasonable. I see a couple of more questions coming up. Let me just
Yeah, Oswald asked, to what extent do you think that reinforcement learning will become relevant to recommender systems in the future?
That's a great question by Oswald. So it's already super relevant. I was going to come up with that. Usually, what happens is once once you've reached like a sort of good static baseline, there's a good chance the ability to improve it um, comes from the ability to improve it comes from you having collecting that reinforcement, that reward or that penalty to tap back into your algorithms. These formulations are run by something called Q learners, and I was actually going to come to this in my next slide, but uh, let's let's go to this red flag 4. Now if you guys are in LinkedIn, I'm pretty sure a lot of you guys want jobs in after COVID ends. Now you see LinkedIn's recommending me 2 jobs. There's one NASA job for mission control systems using deep learning, and there's the other one's the Smith Hanley Associates. I don't know what that is, but it has this reinforcement sort of tab to it, which is, are these jobs good for me? I could vote it thumbs up or thumbs down, and usually this basically goes back into the system, and it's either suppresses if I put thumbs down, or it shows me more of the similar ones if I put a thumbs up. It's a good understanding to convert an unsupervised problem into a supervised problem, where the machines can be taught what is good and what is bad given the context, given the time window, and so on. But these are super relevant in search engines, in recommenders, in control system theory, and so on. You want to build we're not going to get into the theory of reinforcement learning because that's going to be a slight stretch in today's talk. But you never start the system with reinforcement learning. You actually create a future environment with the system that can possibly help you capture more data. So every time you're swiping left on Tinder, it basically goes back to the system and tells the AI that I don't want to see matches like this. I want to see more matches like that. And how do you incorporate that into the whole modeling system, into the whole objective function is sort of the deeper problem. But if someone's interested in learning about RL, you want to look at Q learning methods for rec systems. You want to learn you want to focus on bandit updates. You want to learn at suppression filters, which are more like rule based reinforcement learnings, and so on. I'm not sure if I answered your question, but feel free to follow up. Now,
Yeah, Noral asked, how big an impact do you think Apple's iOS 14 will have on recommendation systems that track across platforms?
yeah, I need to skip this one because
Yeah.
it's sort of like a conflict of interest for me. But because in short, nobody knows how. Uh, but yeah, we'll see like in spring what happens.
Um,
Happy to talk offline, Norel, if you're alluding to something specific.
Yuling asks, is there a way to combine the content-based model and collaborative-based model?
Yes, that's a great question, Yuling. Typically, what you see is you usually go live with one of the either or. Content-based systems are easier to get onto production because it requires like less amount of data. But you usually, once you start collecting more and more data, by when your product gets traction, you move to the collaborative-based approach. And then once you move to the CF-based approach, you try to combine best of both worlds. And these systems are called the blending systems or stacking systems or combinatorics of either or. A really easy way of combining that is Netflix on its first slide gives you a content based model versus on the second slide it gives you a collaborative based model, and then based on which one's winning or which one's not winning, it tries to shuffle it back and forth. So there's different ways of choosing. Different users behave differently or react differently based on what they're shown. But what happens is you need the ability to figure out which user likes which algorithm the most, and that basically becomes a really large A/B testing problem. Awesome. So we have no open questions now. I'll go back to my slides. Now um, we were discussing the caveats of A/B testing. One classic interview question that I love to ask people is what's the simplest way of avoiding a bad A/B test? And a quick solution to that is do an AA test, where if you have two of the same populations, give them the exact same treatment. Don't give them different treatments. Give them the same algorithms, and then measure like what the results are. If the sample sizes are large, you get two wins out of this. One, it teaches you that there's how much bias is there in your populations, because if you show 100 people apples and you show another 100 people apples as well, and let's say one person buys on each group, you're actually good. But if this AA test actually fails, then you save yourself a lot of future trouble. um, you also save yourself you also gain knowledge on like the objective performance of your A/B test, what the bounds of errors are. And then another way of uh, doing this is you want to do these tests several times in different conditions, and this also helps you to measure some of these biases and get more belief. So, for example, if anyone's thrown a dart, if you throw a dart and you get a bullseye, there's a good chance you got lucky in your first chance. So, a good way to sort of play out the variance is throw that dart like 5 times, and if you get a bullseye 4 out of 5 times, you know that okay, why there was a condition where you didn't get a bullseye and so on. So 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 roll the dice pretty often. Don't get super excited. When I was young and I took out my first algorithm, it was for Target for their app called Cartwheel in 2013. I actually got a really good result, and I was so happy with myself, and all the science that I'd learned in class came into fruition. But what happened was when I repeated the test like for more than a month, I saw a lot of temporal like meltdown of the algorithm. It did not survive the test of time, and that initial success eureka moment was sort of diluted by the amount of work that I had to do in the next couple of months to make it more foundationally robust and performant over time. Now, like I said, A/B testing is even harder than building out the algorithm in the first place. Now, this is 2016. Right now, Netflix is A/B testing pipeline is really more advanced, but this is what a practical system looks like. You can, I'm pretty sure, not a lot of you probably don't understand several aspects of what an API is, what a Mesos server is, what Kafka Kinesis is, but this is just to get you like if I have to break this chart down simply, it's you have an API where every Netflix service is actually accessing the API. API is nothing but like a programmatic interface that different services can interact with. So this service is essentially saying that, hey, I want to show this guy this recommender, and then it goes into the AB testing server, and they figure out like whether this recommendation can be A/B tested with which algorithm and so on. They evaluate it, they do some sort of sampling to figure out the biases, and they allocate. They allocate to Sean, let's say, algorithm one, and they allocate to me, algorithm two. That usually goes on. You save all that data, you persist it, you have in disk what you allocated and how you allocated, and then you actually measure whether Sean clicked on his algorithm and whether I clicked on mine, and then you show the world like like how good or bad they are. And that over time, even though it looks simple, like this involves more than 800 people at Netflix to just A/B test more than 500 algorithms that they have, and the winner over time uh, soon takes the position of other algorithms. So imagine this to be like a Kaggle, an internal Kaggle competition at the company. There's a lot of good blog posts on this, so feel free to check out engineering at Netflix. Look at their blogs. They have a special machine learning blog, and they are sort of the gold standard of recommenders. Um Now, another problem that's I believe someone brought up was, how do you actually measure it without going live? So in different companies, whether it's Uber or Lyft, you need your recommender to be evaluated before you actually go live with it, because you leave substantial risk on the table if the recommender goes rogue over time. So You can do that by a technique called visualization and monitoring of rec engines. There is well documented literature as to what you, before you serve these recommenders, what can you learn? How can you unblack box these recommenders? After serving is what everyone's familiar with. It's what we described earlier, but it's also important to understand that, hey, before you actually take your cake out of the oven, can you taste the batter? Can you taste the cream cheese? Can you taste the condiments on top? Can you taste your nuts? Because there's a good chance that, if there's some bitter nuts, or if the frosting is bad, uh, if it's gone bad even before you put it in the oven, then you actually can save a lot of trouble of baking that cake off, because the whole cake's going to be spoiled if let's say you've added salt instead of sugar in your batter, and so on. So I know the analogy is pretty poor, but I hope you guys get the point. uh, Now here's one classic visualization that the industry follows. What you see on the first chart is how many items were recommended each time. It's sort of a classic frequency distribution histogram, where you can see on the a long tail. This long tail distribution is one of the prerequisites of building good recommenders. What it's showing is that there's enough coverage and enough exploration exploitation of you to recommend. If these long tails are not really long and they're very sort of right skewed or left skewed, then you know that there's a very very fundamental problem where your recommender is not capturing properties of the users or the items. So Spotify earlier, I'm not sure if you guys are young enough, but when Spotify started, they would recommend the same songs over and over again. The same US top 40 hits would show up in every playlist. And soon they recognized, like, they were paying out millions of dollars to these top 40 artists, because for every play, they would get, basically, they would have to pay a small amount to the artist. And they realized none of the other top 40 artists were actually gaining any money. But then people definitely wanted to listen it, so they were causing the Claudia problem, if I can use her name. That, hey, why am I being recommended the same songs? So they came up with this whole exploration and sort of like uh, novelty aspect, where I can show you something novel that you might like based on certain properties. So this first chart captures that. The other ones are like, okay, how many users am I going to recommend this to? And it's like, hey, there's 20 million users, 20.5 million users that this is going to go out to. There's about 395 unique items that's going to go out to them. There's 2 million people that don't have enough recommendations to show for. There's some other names of the top items that I want to set out, and so on. There's like, let's say with COVID, number 4, the adult coloring books are like coming up. So you can see, like, what are the top items. You can scroll down and see more. There's some diversity metrics which Claudia brought up, that people measure. It's sort of like a good way to understand how much novelty you can see. um, there's uh, there's some other temporal metrics, which is like, hey, over time, how are these metrics changing? Like, what are the percentages lifts? What are the frequency graphs? uh, and so on. And these are more of uh, offline evaluations before you send them out. So it's basically doing a postmortem or a diagnosis on what your recommender looks like. Usually you have some quality assurance teams looking into this and seeing, like, whether this actually makes sense or not, and how off are these as compared to other algorithms. We ran through these. Now before I go to the next slide, I have one Q&A. It's
Yes, Reka asks, in your fitness challenge example, wouldn't the control also have the same bias?
the fitness. Yeah, so you need the whole motivation of using that fitness example was to show that you need to actually control that bias. So if you actually did not have that, then that would be a problem. But imagine like if you did a 50-50 split, and the other algorithm uh, had uh, had that sort of brownie conditions as well. then sometimes what happens is in certain conditions, certain algorithmic biases do not show up. So that usually comes over. That's usually reflected over a period of time. So my motivation to say that was, hey, during that week, our algorithm did better because it only does better once there's an exogenous factor that assists that algorithm. Versus the other algorithm did not really was not super manipulated by the 100-day fitness challenge. But when we fast forwarded that to a couple of weeks ahead, when the whole fatigue was checking in with the 100-day challenge, you notice that the other algorithm was actually doing far more better because the the one that seemed to be really good was not assisted by this whole social media surge and so on. And that's primarily because, let's say, the other algorithm was mining onto the social media data, but the control algorithm wasn't did not have access to that data, or was capturing some different properties of the data.
Oswald asks, are random recommendations selected from the most popular categories?
Yes, that's one of my favorite algorithms, actually, because you can get that started in a few lines of code. uh, and if you allow a pre-filter condition, which is, hey, let me recommend you the top 10 movies at Netflix uh, that are trending in the last 100 days, and you can do a random top 10 pick out of like 50 or something. Now that's a classic exploitation problem, where you exploit by choosing the top 100, but you show the a random sample of 10 every day. And that is almost for every baseline algorithm. That is the gold standard of setting a relative baseline. So if you can't do better than a random set of top items, then you really are not adding too much value by machine learning and AI. Um, uh,
Katie asks, do you feel that recommendation systems have a role in the medical field? And if so, what limitations do you see? And how can you make the best model that takes into account the human experience?
Yeah, that's a good question. I've worked with about 4 or 5 medical devices company as well as prescription companies. Now, with medicine, there comes large amount of compliances, both HIPAA compliances as well as governmental and FDA regulations. So, finance and medicine are the two trickiest sort of components. However, there's one client called GoodRx. I'm not sure if anyone's used it, but they effectively recommend you a different formulation of medicine, which is like, hey, if you want to, let's say, buy Adderall or buy, let's say, aspirin, what's the closest store that you can buy for the cheapest price? So the recommended formulation is converted into like a search formulation. Like, let me recommend you a store which is not a CVS and not a Walgreens, but something else that's closer to you and cheaper than you. So the recommender has constraints of like pricing as well as distance. That's one. The second one is more around treatments. So if you go to WebMD and you search for like, hey, I have a headache. What do you think? What problems do I have? Now within WebMD, you can actually get recommended other people who are having the same problems with the same diagnosis that you actually wrote. So there's a lot of text matching between your question that you asked and the other questions that actually help you understand the medical conditions. These are the vocabulary of these uh, systems are completely different because medicine is a new language by itself. So there's a lot of NLP studies on it as well. Now I could keep going on and on, but there's a huge potential of tapping onto both recommenders and search systems to build efficiencies within the system, both in diagnosis of diseases as well as finding answers and finding solutions to your medical problems. Awesome. We did run through the duplication problem. Um so one thing that I want to sort of get the point across as well is, we've seen a lot of rules, right, or a lot of algorithms that we covered for news, for medicine, for ecom, for Netflix, for media. one thing that you guys need to be sure of is uh, like if it works for like Amazon, right? It's not necessary that it's going to work for another company. For example, uh, if Quora, which is a question answering website, when they use the same algorithm as Amazon, which is people who bought this also bought that, or people who read this question also read that question, it doesn't really work for Reddit or Quora, because Reddit and Quora is more about like the exploration. Like people are going to Reddit to explore new topics. It's sort of like a fun element. There's like an engagement, a community sort of element to these websites. So you want to basically be sure of what business you're actually covering, and then make the AI from the bottom up. Go from the business rules and then bake that into the AI. If you actually flip the question, if you flip the formulation, then you actually it leads to like poorer systems that you actually could have avoided. For example, in e-commerce, right? It's important to understand what's the marketing aspect of the product, what's the revenue. You need to identify diversity. You need to get sizing correct. You need to get delivery correct. So all those need to be baked into the e-commerce recommender. A really good item with a poor Amazon Prime delivery will not be recommended. So understanding those business rules and incorporating those features is also important. For news and media like Netflix or CNN or Fox News, it's important to understand the trending and recency nature of recommenders. You can't show, even if it was a breaking news, but it was 5 days ago, you really can't show that as a recommender right now. So how do you incorporate recency as a core first class citizen in your recommender? Similarly, for job sites, if I'm looking for a new job, what I showed you on LinkedIn was the relevancy and the descriptions matter, but also the hierarchy. Like if I'm looking for a managerial position, I do not want a summer intern position, even though both of them might be a machine learning position. The hierarchy is also important in job sites, but the hierarchy is sort of not important in like a news site because there's not really a hierarchical approach to content. Similarly, for travel and ticketing, pricing is one of the pricing and speed is one of the most important aspects of recommending. So if Expedia or like Priceline is recommending something to you, they usually recommend you on a combinatorics of price and speed. Can you get from LA to San Francisco within 1 hour in less than $100 is sort of more important to the user than okay, can I fly first class with the best caviar and champagne in my flight? That's not what people are looking for, and so on. So think about these business rules. Think about what you want like from the business and how that relates to the AI. The second one is I just took a screenshot of what YouTube shows me, and you can see like I get a bunch of Gordon Ramsay on the left, and then YouTube is trying its best to sort of explore some content. Now YouTube recommenders are also gold standards in recommendations, and you can see that uh, it's trying to either show me cooking shows about Gordon Ramsay or it's trying to show me some other stuff, some shows that I watched, like the Silicon Valley show or something. And then it's showing me some action stuff related to camping and so on. So it's figured out like the 3 4 categories that I'm actually watching, and it gives me like the top curated content from each. Uh, and this is commonly called the serendipity problem, and they do a really good job in understanding whether you want to move to the next category or move somewhere. But however, like this does not really apply to LinkedIn, right? LinkedIn does the same thing where it tries to show me a relevant position as a full stack engineer or a data engineer, but I'm essentially looking like only at a data science position. So what that could imply is, when you explore here, you really don't do a good job because there's no chance of me moving away to like another sort of category of employment. Then the next one I believe Oswald asked this question on reinforcement, and this is uh, what we what we see as a red flag. Not a lot of recommenders incorporate the feedback from the users, and that's a function of engineering teams, UI teams, the ability to show that the forms or the thumbs up, thumbs down to capture or the ratings. So when those things are lacking, you usually struggle with improving the recommenders over time. Now, this is a classic modern rec pipeline. Um, it's obviously in many different layers, but I try to break it down into a data ingestion layer, which is on the left. Now, usually you have behavioral data coming through, transaction data coming through, third-party data. Every data source that you can mine onto, you essentially tap onto these data ingestion layers. There are large data engineering teams, software engineering teams that are responsible of capturing this data with low latency and high fidelity. And these data points are pushed through messaging queues, through importers, through sharded databases, and they're stored like on the cloud usually these days, or like on some persist medium like HDFS, a hard disk or something. There's several Hadoop systems that can store this data and process it. And then once this data is nicely massaged, clean, salt and pepper is added to some of these data points, then you make that available for your machine intelligence layer. That's when the data analysts, the data scientists, the data engineers also come into play, and they generate these rec algorithms from this data. They represent these user item features in the feature generator. They have these reduction rules of taking the rec algorithms and applying more business rules on top. And then the whole reporting and analysis of like what these recommender algorithms are doing, measure like, there's no rogue recommenders, and then you finally push that back to the A/B test and take the feedback and incorporate it back to the recommenders. So it's sort of like large systems, and usually like data science is a team sport. So always think about like, where you fit into this puzzle. What aspects of these systems are not only applicable to recommendations, they're applicable to other systems as well, like forecasting, like finance, even like fraud detection and so on. They typically follow this left to right mechanisms of data flow. So you want to understand like which aspects are you most familiar with. But the truly successful data scientists are the ones that think about this as a team sport. They just don't think about it from the mathematical formulation. You have to think about it from the business perspective as well as the teaming perspective, like who does what and when. And it needs to be a really cohesive vehicle, like, to get to a fidelity like Netflix or Facebook, where large teams come in and own these systems, and they do a fantastic job in delivering day in and day out for each other. Nice. Some of the references that I've given are here. I'll try to update them. uh, that was pretty much it on my side. I know we're over an hour, but definitely wanna keep the Q&As coming for another 2-3 minutes if possible.
Yes, thank you, Vedant. We'll spend some time now answering your questions. First of all, Hashnit and Norel have two questions about sample size. Hashnit asks, how do you deal with data scarcity? For instance, if you have very few people who like both Titanic and The Matrix, how do you handle that?
Oh, that's a really good question. So this is classically known as the cold start problem in recommenders. So Harshneet is bringing out a case where, let's say, a new movie was released. Let's say the new Star Wars movie came out next week, and there wouldn't be enough examples of Star Wars with other movies. So how does even Star Wars get seeded into this whole data ecosystem? And that typically happens by giving Star Wars a sort of initial push, where you have some exploration capacity to explore these cold start users. You could either do that, and that's what the bandit cold start problem gives you. You show the new movie to a few users, collect feedback. If it's good, you push that up, and so on. And the second way is to mine the relevant information of the new Star Wars movie with past historical Star Wars movies or relevant movies. And you can do that by understanding who the cast is. Is it a Lucasfilm? Is it how much is the budget? So if it's a really high budget movie, and the previous high budget movies did really well in your recommenders, you actually give it a higher seeding score. And typically, once you get that past a few thousand users, you can actually see that those things are now picking up by the recommender. So it becomes a chicken and egg problem. Um, and then once it gets picked up, you have enough juice for the next iteration of the recommender for it to propagate, and it can live by its own. Like it can have its own badge and score.
Norel asked, what kind of sample size do you need for a good A/B test? And does that vary according to the type of action you're looking for?
Yeah, usually I'm not going to dive too much into the nitty gritty of the stats, but some of the tests that you want to ensure, some of the strong, robust tests that you want to ensure is a two-tailed test, a t-test. Sometimes because it's a binary indicator, you want to use beta distributions to model a yes or no decisions. But that's the sign of a good data scientist, that they are able to effectively communicate as to what the sample size is. The sample size is determined by you, and for each sample size you actually tell the stakeholders what confidence do you have in this. So there's no correct answer for that, but I think the question should be, uh, what are some techniques where you can estimate what sample size is important to you? And those are typically either a p-value test or a two-tailed t-test, or any sort of binary test indicators that you can actually showcase. It's important to, because the decision is a binary outcome, whether you watch the movie or didn't watch the movie, it is slightly different from classical univariate comparisons. So you can look up some similar tests like a chi-square test, or maybe maybe some beta a hypergeometric test that can actually understand uh, how much did your population change, or what would be your sample size, what would happen if your sample size reduced by 10% or increased by 10%. Just to throw a number at it, it needs to be in the few thousands at least, just because the reward actions are so low. Once you show an impression million times, you get a few buys. So if you're doing an A/B test on the buy, it needs to be usually in the few thousands.
Yeah, Oswald asks, in your previous diagram, where would you place the issue of data drift?
Yeah, usually the data drift would be incorporated as a feature by itself, where you could do it in one of two ways. When you're generating the features, you could have certain features that correspond to the drift, so that your algorithms actually learns the importance of the drift in your business. The second way is actually explicitly in that feedback loop, tying a drift component. Uh, uh, it's much easier to do that on the feature layer itself. So let's say the Bernie Sanders mittens are losing sort of the impact over time. Let's say last week it was selling 1,000 units an hour. Now it's at 30 units an hour. So that differential change can be a drift feature in your uh, item feature. And if the velocity of change or the acceleration is negative, your algorithms based on the convex formulation can actually learn that uh, these drift features are are used to not recommend these mittens anymore, and so on.
Okay, let's give it you a couple more minutes to ask more questions, and then we'll wrap this up. Okay, doesn't look like we have any more questions. So thank you so much, Vedant. That was a fascinating talk. And I want to thank everyone for their attendance. And I look forward to seeing you in our future seminars. Thank you so much.
Thank you, guys. Thanks for having
Thank
me.
you. It was a great talk. Thank you.